I'm Victoria. I'm here in Oslo now, working as a PhD student at the Department of Chemistry at the University of Oslo. My supervisor, Reidar Lund, is also here in the audience. And we are primarily physical chemists, I would say more. I understand that many of you are more towards the biology side, so more like biochemists and such, but we don't work so much with the proteins ourselves, but we will get to that. But today we will talk about this paper that we recently published, where we used small angle X-ray scattering to characterize the different intermediates in this styrene malic acid lipoparticle formation from them lipid bilayers. So, as I said, we are from the Department of Chemistry here. You can see here an overview of some of the campus. So I can get my laser pointer here, and the two frontmost sort of donut buildings here are the Department of Chemistry where we are, and we are part of this research section called the BioCubed, which is chemical life sciences, and it consists then of this bioanalytics groups, the structural biology group, and then us, and we are then more the soft matter group, I would characterize this as. So in the soft matter group, we then explore more these self-assembled systems and the fundamental mechanisms and processes that are related to these. So here's Reidar, who's the supervisor of the groups, and our research is then mainly focused on understanding the basic structures and dynamic processes of these type of assemblies, such as micelles, peptides and polymer nanostructures, and lipid membrane interactions. Importantly, our group is we have quite a lot of experience within scattering techniques for studying these processes, particularly then small angle X-ray and neutron scattering. So looking more into details, some of our projects, so you have some idea of what we do. One of our larger projects is where we are studying the mechanism of these antimicrobial peptides, and particularly their interactions with lipid membranes. In connection with this, we also have some projects where they study peptide and peptoid-based nanostructures. One very large part of much of our research is the study of these structures and the kinetics pathways of self-assembly, which contains many different types of systems. It includes much of my research as well. And we're also interested in polymer, so the structure, thermodynamics, and dynamics of polymer assemblies. Now, when it comes to my project, they have been mostly focused on these surfactant or detergent interaction and kinetics. So one of my main rather large projects is studying these pathways of solubilization and interaction of detergents with lipid membranes. So I started out studying these classical detergents such as SDS and Triton X100, and then as we were applying for experimental time at different synchrotrons and reactors, one of the feedback that we got was this request that we're also studying these more newer techniques for solubilizing membrane proteins, such as this styrene malic acid copolymer. So we therefore decided to include this in the project here, which is the origin of this paper. Now, another project I'm working on is regarding the assembly kinetics of photocontrollable surfactants, where I then use molecular dynamics to study then the kinetics and thermodynamics of both the assembly and the photoisomerization event in these systems, and comparing them directly with scattering experiments. We also have hopefully a paper that will come out soon on these mixed aggregates of lipid and photocontrollable surfactant and how they respond over time to the light triggering events and how the morphologies in the aggregates change. But today we will then be talking about the styrene malic acid copolymer and how it forms these nanodiscs from bilayers. So as mentioned, we decided to include this copolymer in our solubilization project, but since we didn't have any expertise on this ourselves, we sought out our colleague from the Institute of Biosciences, Marcella, who have been working on this system before. So probably some of you are familiar with some of her papers here. So she has this quite early paper where they characterize this lipodisc SMA 3:1 copolymer when it formed these nanodiscs from DMPC bilayers, using then techniques such as DLS, cryo-TEM, and EPR and DSC. Now the second one here is where they used the same copolymer, but then incorporated this bacterial rhodopsin protein in the nanodiscs and compared then the structural and dynamic properties of the protein in the nanodiscs. Now in this final paper, they investigated again this SMA 3:1 copolymer, adding them then to supported the lipid bilayers, as well as surface adherent giant unilamellar liposomes. And then they used this confocal microscopy and surface acoustic wave resonance technique to show this evidence of pore formation in these supported bilayers, as well as vesicle deformation in the liposomes. So with that background, we then wanted to investigate the intermediates that are in the pathway from these mixed vesicles with the SMA 3:1 polymer, going from that to the fully solubilized nanodiscs. And we also wanted to see what's the effect of temperature and varying the lipid type. So the technique we use for many projects, for that matter, in our group, but also for this, that we find is optimal for these types of studies, is small angle X-ray scattering. So as some of you aren't probably experts in this, or maybe haven't used this technique before, I will go through it in some details, although I see there are some people in the audience who know it quite well. So what is the small angle scattering? So probably most of you are familiar with some type of diffraction experiments or scattering experiments. So as in any scattering experiment, you will have a source of radiation of X-ray in this case, and you will have to select your wavelength and align your beam here. And then you will have your sample where the radiation is hitting. And in the case of SAXS, your sample, importantly, can be in a number of different states and environments as you choose. And also importantly, the detector where you actually detect the scattering in SAXS obviously needs to be quite far away from where the sample is, so that we can actually detect then the scattering, the difference in scattering at these very small angles. So if we have a sample, such as in the example here, where you have, for example, vesicles in a solution, then you will get this isotropic scattering pattern. So it's only dependent on the scattering angle here, what the scattering is. So in that case, we will then do this radial averaging of this two-dimensional detector image, and we will get this one-dimensional curve where you have the intensity as a function of Q here. And this Q vector, importantly, as you can see, it includes the information both on the wavelength and on the scattering angle here. So if we actually look at this, also combine this definition of Q vector with Bragg's law, which probably most of you are familiar with, we will see that this Q value is reciprocal to the real space distances. So that means when we are looking at the small Q values, we are looking at very large distances in real space. Importantly, also, when we do solution X-ray scattering, such as here, we will also measure the solvent that we are using to solvate our sample, so that we can actually subtract the scattering from just the solvent from that of the solution. So then we will end up with a scattering curve that looks something like this. And this you will also normalize to what is called absolute scale, so that it is independent of the instrument. And you will do this by including a measurement of some sort of known standard, like water, for example. So all the data that is presented here and was presented in the article was collected at the SAXS instrument called P12 at Deutsches Elektronenzentrum in Hamburg, Germany. And also we ran tests at our in-house SAXS instrument operated then by the Rex lab in Oslo. So the question then is, why do we use SAXS? So here I want to just present some arguments as to why we used it in this case, and also potentially why you might want to use it yourself in the future. So first of all, SAXS probes the nanoscale structures, and it does it in situ. So it doesn't require any specific pre-treatment of the sample. It also requires quite little sample. And in addition, it's quite a non-invasive technique. So even though if you go to synchrotron, you do have to monitor the radiation damage to your sample, in general, you can recover the sample and you can study the exact same sample with other techniques afterwards. So this means that for soft systems, such as the ones we study, it's optimal because we can study them exactly as they are in their native environment. Now, another benefit is that this can obviously then be combined with the variety of techniques for perturbing your system. So if you want to change the temperature, if you want to apply pressure to your sample, if you want to stretch your sample, if you want to apply an electric field, if you want to do rheology while studying your sample, all of this is possible to do while still doing the small angle X-ray scattering. Also, with the new and very bright synchrotron sources we're getting, we can also study these very short time scale out of equilibrium processes down to time scales of milliseconds or even microseconds, actually. So this then allows us to study, for example, intermediates in the self-assembly processes, or solubilization processes using then small angle X-ray scattering in combination with this stuff flow device for rapidly mixing the solutions. Now, we say that we can study the structure on a nanoscale, but how do we actually get this information from this one-dimensional curve? So there are some model-independent approaches to SAXS data that can get you some limited information, such as, for example, the radius of gyration, if it's possible, for the particular size. But the way to get the most information on the structure is to use analytical modeling. So this requires then that you have some idea of what your particle looks like. So in the case of lipid vesicles, for example, we're pretty sure that this is a spherical double bilayer structure. So we can make a model for it in real space. And from this, we can then deduce how such a structure would scatter. And this will then give us an expression for this one-dimensional curve, which will then include both known parameters, such as the molecular volume of your molecules, the electron density of your molecules, the concentration, etc. And also these unknown parameters, such as in the case of a vesicle, could be like the radius, the thicknesses of the bilayer, etc. And these unknown parameters you will then fit to the experimental curve. So if this, if your model of choice actually matches then the experimental data within, of course, reasonable physical parameters, which you have to make sure of that you're not fitting it to nonsense parameters, then you're all good, and you know, you have your structure and you can publish the data. However, if it doesn't fit your experimental data, then you have to go back and reformulate your model. It could be that the model requires more detail, or it could be that it's a completely different structure. And perhaps in that case, you will have to investigate it further using then other methods to try and deduce what kind of structure it is. So this just shows that this is very much an iterative process, unless you're very sure, of course, about the nanoscale structure. But in that case, it might not be so interesting to study it if you already know it. So when it comes to this analytical expression and for the normalized intensity as a function of Q, if we here assume first just that we have a homogeneous particle, we can split it up as follows. So first of all, we have the number density and the volume of the particle, both of which should be, you should be able to calculate then from the molecular volumes of your molecules and the concentration, which is also why it's important to keep your scattering intensity on an absolute scale, so to measure that standard. Then we have what is called the contrast of the sample, which is the difference then in the scattering length density. In the case of X-rays, this will be the difference in the electron density of your material to the solvent or to whatever environment it is in. And the next term is the Q-dependent term, and it is referred to as the form factor. And this describes then the Q variation in scattering that occurs due to then the shape and size of your particle. And then finally, we will have what is referred to as the structure factor. And this is what in SAXS this refers to then interactions between the nanoscopic particles. Generally, if this is you know, repulsive or attractive interactions that occur between these nano structures in solution, you can generally avoid this term by keeping your solution very dilute. because in that case the particles will be so well separated in the solution that you won't get any effect of these interactions. So before moving on, I want to discuss just a little bit extra the concept of contrast, because it's very important in the case of a lipid bilayer. So if we have a lipid bilayer in SAXS, it's normal to then divide this lipid molecule in the very simplest models. It's normal to divide it into these two parts, where you have the head group, which is electron dense, and then you have the tail groups, which are more electron poor than. So that if you look at then the sort of electron density profile here across a bilayer, it will look something like this. And because of these large differences, this the bilayer is very sensitive to any insertion of a material that has a different electron density. In addition, it will be sensitive to the phase transitions, because as the bilayer undergoes a phase transition, then the volume of these tail groups will change, and that will also change then the electron density of that group. So this is quite important for, and it's an important reason that SAXS is quite a good technique for studying lipid bilayers and interactions with lipid bilayers. So now I just wanted to show you some general, very general qualitative things that I look for when I'm studying solubilization, or sort of the simplest thing I look for when I'm studying it. So here you can see the scattering, a typical scattering curve for a lipid vesicle. So here in the low Q region, you will see, you will be able to deduce information about the radius and the polydispersity of your sample. Whereas in the high Q region here, you will deduce information about the structure of the bilayer. So this could be the length of the head group region versus the tail group region, for example. And importantly, if you have multilamellar liposomes, if you have quite a lot of multilamellar liposomes, you will start to see these Bragg peaks in the bilayer scattering. This is then due to the interference that occurs between this periodic bilayer structure then. So that's something to recognize as well. Now, when the structure is solubilized, if you assume, well, normally you will assume that the solubilized structure is smaller than the starting lipid vesicles. Of course, that is sort of the point of solubilization in many ways. So then you will see, most importantly, you will see if it's quite a lot smaller, you will see that the scattering here at low Q will start to flatten out, so that you have a constant scattering here. And if they are also solubilized into these sort of micelles, as is shown here, then also obviously there will be a huge change in this bilayer scattering, or from this bilayer scattering to the scattering of typical micelle here. So then we move on to the actual experiments that we did. So for this experiment, we then decided on, also based on what Marcella had done in previous articles, of course, but we decided to use these two lipids, DMPC, because then we could also study the effect of the phase transition here, and POPC, which also is unsaturated, so you could study the effect of that, and also it is perhaps more biologically relevant lipid. So what we did is we just had the pure components and mixtures then of DMPC with different concentrations of SMA 3:1. So this is the SMA 3:1 from the lipid product here. And we took mixtures of DMPC and SMA as well as the pure components, and we measured those at 37 and 18 degrees, separate mixtures. So not the same one, but they were mixed at the same temperatures as they were measured. And then we had POPC mixtures only then measured at 37, since POPC will anyway be above the melting point at all these temperatures. So if we first look at just the SAXS measurements of the SMA polymer by itself, then maybe a first assumption that you might make about a polymer is that it could be a random coil in the solution. If you compare this, of course, with the scattering, you see that it's quite a different pattern. So likely this is not a random coil. So instead we use this globular collapsed model for the polymer, which fitted quite well to the experimental data. Could also deduce this from looking at the pair distribution function. If you do this inverse Fourier transform analysis of your experimental data, you see also that this is a more compact structure. It's not an extended structure. Importantly, we also had to add this concentration dependent background to our model, which we then assume originates from what is called blob scattering, where you have small copolymer segments that are locally swollen by the water. But also from the local contrast between the monomer units that are then outside the resolution. Now we can actually see the structure from it in SAXS. Now we also have this upturn at the low Q values, which is indicative of some undefined large aggregates that are outside the resolution we have in these SAXS experiments then. Now we do know that this polymer is quite polydisperse, and the synthesis might lead to some very large polystyrene segments, which will then have much lower solubility, and that might contribute to this sort of undefined aggregates here. The scattering of these aggregates can be, or has in this case, be approximated by a very simple structure factor, and it reveals that there are very few of them, and also this is kind of seen from the fact that it doesn't have a constant variation here with the concentration. So the scattering intensity from these aggregates actually varies a bit randomly with the concentration here. Now moving on to the measurements of the mixtures, I first just want to point out, first of all, that these curves have been scaled. So they've been logarithmically scaled here. So if I had plotted them all in the same plot without scaling them, they would very much overlap. We would have been able to see all of them, which is why it's presented in this way. The first thing that we can notice is that most of them seem to start to flatten out here at the highest concentration, which is indicative of them being solubilized into these smaller structures, right? But interestingly, the DMPC at 18 degrees, so below the phase transition, seems to flatten out earlier or at lower SMA concentrations compared to DMPC at 37, and also compared to POPC. So this is very indicative of DMPC then solubilizing at lower concentrations when it is at 18 degrees compared to 37. So this is something we can see just qualitatively from the data. Another thing is this change in the contrast of the total contrast of the lipid vesicles with the solvent. Especially you can see it here for POPC, which has very low contrast here in the beginning, and then as you add more SMA, the contrast increases here. And this is indicative in all the cases that SMA is being absorbed onto the lipid vesicles in some manner. Also, interestingly, in the pure POPC lipid vesicles, we have quite defined Bragg peaks here. So they have quite a large fraction of multilamellar vesicles. But this multilamellarity decreases as we increase the SMA concentration without seemingly disrupting the vesicle scattering here. So those were just some qualitative observations that we can make from the scattering data. So over to the modeling. So in the case of the pure lipid vesicles, we have used this much used model for lipid vesicles, which is the 3-shell model, where we model the vesicle structure as one outer shell corresponding to then the outer head groups, one middle shell here, which corresponds to the tail group region, and then an inner shell, which corresponds to the inner head group region. And this is then defined by the scattering length density that is calculated from, of course, the tail of the lipid in question and the head group of the lipid in question. So that's how we define the scattering length densities of each shell. Importantly, we also have to then account for the multilamellarity. So this uses then the same model, but it also includes then a paracrystalline structure factor to account for the interference between the bilayers here. When it comes to the vesicles that have absorbed SMA, and we did assume in all the modeling that all the SMA had been absorbed, both on the basis of trying to add free SMA in the model and it not fitting, and also on the basis of other research showing that all the SMA will absorb onto lipid bilayers when in the presence of it. So for the lipid vesicles that had absorbed SMA in it, but were still lipid vesicles, we extended this 3-shell model to a 4-shell model so that we could allow then an asymmetric insertion of SMA into the bilayer. And in this case, we calculate the scattering length densities by creating sort of a pseudo molecule here, which consists then of the lipid along with some fraction of the SMA polymer. So for the head group, we will then calculate it as the head group plus some fraction of the malic acid. And for the tail group, we will then calculate it as the tail group electron density plus the electron density from a fraction of styrene units. Now we also allowed in the model for styrene units to be in the head group, but in all the fits, they all wanted to be inserted into the tail group region. So essentially they are all in the tail group region. Now for the nanodiscs themselves, we started out by basing our model on this, which has been used for the MSP nanodiscs, where you have this lipid bilayer disc, where then the scattering length densities will be calculated just as in the lipid vesicle model, and then you will add on this belt, which then theoretically should contain the SMA polymer around it. Now this did not fit to our experimental data, so we therefore allowed still the SMA to distribute in the head group or in the lateral plane here of the disc, also when they are solubilized in these nanodiscs, the same way that we included them in the vesicle structure, so that you have some fraction of SMA that is then distributed in the plane of the disc here, and then a fraction that is distributed as a belt around the disc. In addition, we also allowed styrene units to insert into the tail region from then this belt structure. Importantly, I want to mention that we did try different models, just to check that there were no other models that actually fitted the data. So, for example, this ellipsoidal core shell mixed micelles, which I guess no one was expecting it to be, hopefully at least. Also the original one, and just a mixed disc structure without any belt structure on it. But as you can see, none of them really seem to represent the data as well as this mixed disc with the belt model. So that is the one that we ended up with then for all the data sets. I have to mention it's also difficult to represent fits for a model that doesn't really fit to the data. So for many of these, they weren't giving them physically correct parameters when you're fitting them. So then I would just go through and summarize the fits, the results from the fit analysis. So first we had then the lipid vesicles that are well described by this three-shell model, not so surprisingly. And then you can here see the curves where this mixed vesicle structure was fitted to the data, and also notice that the range here for this type of structure is quite a lot larger for the DMPC at 37 degrees compared to at 18 degrees. We then had a region where we had to apply a sum of mixed vesicles and disc model, since neither one of them could accurately describe the results alone. So in this case, we will then have coexistence of the two structures in the solution. And then finally, we have the solubilized nanodiscs, where we again see here that for DMPC at 18 degrees, the nanodisc, the finally solubilized nanodisc alone appears here at lower concentrations of SMA compared to at 37 degrees. For POPC, we again have the lipid vesicles accurately described by this three-shell model, although obviously we have a much higher fraction of multilamellar liposomes present. And we then have this region where we have fitted it to the mixed vesicle structure, where we see this gradual decrease in the multilamellar scattering without having then any appearance of nanodisc scattering. So this means that the multilamellar structures somehow transform into these unilamellar structures without losing then the integrity of the bilayer. So somehow the SMA manages seemingly to fracture the bilayer so that these multi-layers can separate and somehow reform afterwards. And after this, we again just have this coexistence region and then the final disc structure. So looking more in detail on these results, first of all, when we compare, as we have already spoken about, when we compare here the onset and completion of solubilization for DMPC at 18 degrees to that of DMPC at 37 and for POPC, we see that both the onset and the completion happens at much lower SMA concentrations for DMPC at the lower temperature. Now, this result understandably seems quite counterintuitive. It has, however, been reported for this SMA 3:1 polymer before with DMPC. And as I mentioned, it's also quite independent, really, of our model analysis. So I feel like it's a pretty reliable result. The likely explanation that has been presented before, and also we support, is that the lipids then in the gel phase have then a lower tolerance for these packing defects that can be introduced by inserting the styrene units into the lipid tail region, compared to then the liquid crystalline phase, where the lipid bilayer seemingly can more easily recover from these membrane defects, causing then rather a restructuring of the bilayer as opposed to solubilization into nanodiscs. Additionally, we can see a slight tendency that POPC seems to be more resistant to solubilization. Again, seen by the seemingly increased SMA concentration that is necessary to actually induce solubilization here. So the model fits also revealed an increase in the lipid volumes with increasing SMA insertion. So this is an increase in then the volume that the lipid tails occupy in the bilayer. And this increase is quite large, and it's quite similar for actually all the different systems. And it is comparable to the volume change that occurs upon a phase transition in the lipids. Likely, this increased volume is again due to the defects, or due to the lipids then being affected by the inserted styrene units, so that this creates then packing deficiencies in the lipid bilayer. It might also support the previous calorimetry measurements that have been done, showing this very broad transition, phase transition of the nanodiscs, since this increased volume effect also persists in the resultant solubilized nanodiscs. So finally, the final solubilized nanodiscs then, if we are looking at the ones where we are in the complete solubilization regime, we do see that their sizes will vary with having a radius of 40 down to 23, then depending on the SMA concentration, so that you have smaller discs the more SMA you add to the solution. This is just the radius of then the lipid bilayer part. And in addition, the belt thickness will vary between 9 and 15 angstrom, again depending on how much SMA is used, but of course also depending on the lipid type, due to the difference in how much SMA they could actually incorporate in the bilayer structure. So they also have quite high, relatively quite high polydispersities with a PDI between 1 and 1.6. And all this, these sizes, they fit quite well with what was found previously for this polymer. With the nanodisc, then they found it to have an average diameter of 9 nanometers, so 90 angstrom. But also that it had a very large range of sizes from 5 to 15 meters, as they found from the cryotem here. Now, we also saw that the total amount of SMA that was distributed in the surface of the disc seemed to flatten out as the discs started forming here, indicating then that after saturation, the excess SMA will then go to form the belt around the disc. So with that, we made this figure to try to summarize all of our results. Overall, it seems as if the SMA solubilization sort of follows the classical steps of solubilization, where you first have partition of the polymer in the bilayer, followed by a coexistence regime, and then the complete solubilization into nanodiscs. It also seems that the bilayer can fracture already before complete saturation occurs, as we could see from the decrease in the scattering from multilamellar structures. The DMPC lipid bilayers are saturated with SMA and solubilized at lower concentrations when they are below the transition temperature. Also, it seems that the POPC lipid bilayers have a higher resistance towards solubilization by SMA 3-1 compared to DMPC. We found that the lipid acyl chain packing is disrupted by the SMA 3-1 insertion, as indicated by the increase in the volume of the lipid tails, and also that this distribution of SMA on the surface of the bilayer, or lateral distribution of SMA, then persists in the solubilized discs as well, so that it's the excess SMA that actually goes on to form this belt structure around the discs. So with that, if you're interested further, I refer you to this article, which I hope you want to read, or perhaps you already read it. And of course, I want to acknowledge then my co-authors. We've all done a really hard work on this article, so we are happy that it's being noticed. Also, some of my colleagues that have been supporting me, and of course the DESI for giving us beam time, and the beamline scientists for helping during the experiment, and the Rex Lab, and of course the Department of Chemistry, who is funding my PhD and therefore essentially funded this project as well. Also, we want to tell you that we have 2 PhD positions coming out soon in our group. So if you know someone who might be interested, then please let them know. And please also feel free to contact us for any questions about this, about any other projects we have, or about just scattering in general, if you want to do some scattering experiments on your in your research. So thank you very much for listening to all of this.
Thank you, Victoria. Great talk. Is there any question for Victoria? I have 3 questions if you know.
Yeah.
Go ahead, Naomi.
Oh, sorry, I muted to say I also have a question, but I'm happy to go second.
So, I go with my first question. Did you try SMA 2-1 and 1-1 just to see the proportion of lateral SMA to the belt SMA would change?
No, I mean, unfortunately, we haven't had the opportunity to do that. It has, of course, been suggested to us, and it's something we would very much like to do. I think it would be very interesting to see actually how different it would look with the other versions of SMA, because they do behave quite differently. Like SMA 2-1 is quite a lot more efficient at solubilizing than SMA 3-1, I believe. So it would be very interesting to study that as well. Unfortunately, we did these experiments in December 2019, and then we haven't really done any big experiments since then, obviously. since we're not allowed to travel anywhere. But definitely it's something I would like to see being done. Would be very interesting.
So I assume DeepMa is also not tried by
What?
DeepMa, the other polymer that is.
Oh, yeah, no.
Okay.
So the question I wanted to ask was, do you think this kind of experimental approach would lend itself well to looking at different lipid mixtures? Because one of the things from the protein point of view that we always come up against is talking about, extracting proteins from different expression systems. And one thing I'm interested in is how the lipid composition would affect solubilization. So not just variation in polymer, but variation in actually the bilayer itself. So yeah, I suppose my question is, do you think that that's something that you could actually kind of get to grips with this type of method?
Yeah, it should definitely not be a problem to do mixtures of different lipids. You should have some control. You should know what the fractions of the different lipids are. We have like in the project with antimicrobial peptides, they are actually doing very complicated mixtures of lipids, but the important thing is to know how much is of which lipid, so that you can more accurately calculate the scattering lengths densities. Because a problem would be if you didn't know that, then you would have another fit parameter in your system, another unknown basically, and the result would be as trustworthy as if you actually know exactly what the composition of your system is. But if it's just testing different lipid mixtures, then that is fully doable, and that is something that we already do. So.
Okay, great, thank you. Oh, I also wanted to say I really enjoyed your description of SAXS. I've done a little bit of SAXS in the past and always just got so confused by
Yeah.
So thank you for presenting it in such a logical and clear way for I don't know, for the biologists amongst us.
Yeah, no, I mean, I have been there myself, so.
Victoria, do you think you can quantify the amount of polymer that is lateral, that is in lateral interaction, and the amount of polymer that is in belts?
Yeah, I mean, it is quantified because in terms of a fraction of the total concentration that we added, right? The problem is, of course, because there is a lot of polydispersity both in the polymer and in the discs themselves. So to say like one number would really be possible. So we can say like on average is this, but it's with then the knowledge that it's difficult to count the number of polymers, for example, because they are so polydispersed. So we can say really there are this many polymers per lipid nanodisc, and also the nanodiscs themselves are quite polydispersed. But it is quantified in terms of the mass of polymer that is actually distributed in the surface and around in the belt. So that is included in the article.
And do you think both of them, I mean, the lateral SMA and the belt SMA, have the same affinity for the membrane?
I mean, it's more a question of the bilayer becoming saturated, I would assume, with the SMA that is laterally distributed, and therefore some SMA has to distribute around in the belt structure then to still sort of keep the hydrophobic parts out of the water, obviously. But if they are different in some other way, it's difficult to say.
So do you think if you have a protein in your lipid bilayer, do you still see the lateral SMA?
Yeah, I mean that is a question, right? It's probably something that is interesting to you guys. I mean, I would assume so, but I'm not exactly sure how inserting the protein affects the nanodisc as a whole entirely. It's something that would also be nice to study further with the structural studies using techniques such as SAXS or neutron scattering could also be very interesting, because then you can do more contrast variations. So yeah, definitely, I think it's probably important for people doing the protein studies to have sort of some of these questions answered, I guess.
Thank you so much.